Hello, everyone. So this video is going to be Chapter 4, Lecture 1. We're going to go over first balancing equations. Okay, so Chapter 4 is on chemical reactions and chemical quantities. So we're going to learn balancing reactions first, and then we'll go into basically stoichiometry. All right, so before we can do stoichiometry, though, right, we got to go to know how to balance. Okay, so last time, end of chapter 3, I kind of introduced to you guys, right, the balancing of the equation. Both sides must have the same number of atoms in order to balance. And if we balance, what we need to do is use coefficients, okay? We do not change the subscripts, okay? Because remember, if you change the subscript, you change the compound, right? So you can't change the subscript. You need to put the 2 in front, right, of the compound. So what you're saying is, okay, there are 2 waters, right? And so in 2 waters, of course, there's going to be 4 hydrogens. So it's easy, you just multiply 2 times 2, right? So just multiply through the coefficient through, and you'll get how many atoms there are, right? So in 2 waters, there's 4 hydrogen and there's 2 oxygens. In 2O2, right, 2 separate O2 molecules, you have a total of 4 oxygens. Okay, so that's how you read that. That's the notation. And so you should get used to using those coefficients. And again, do not change the subscripts. Okay. So to balance equation, I'm going to show you guys a method in order to do this. It's on Canvas. Let me show you where to find it. You go to Canvas and scroll to chapter 4. You guys see that under the lecture material, there's balancing equations Word document. Okay. And so you can just download that. All right. It's 5 steps. Just go ahead and download that and have it, on a separate screen as we are doing these examples so we can follow these steps. So it's basically, step 1, you start with the most complex molecule, which means the molecule with the most different types of atoms or the most number of atoms, right? You're going to balance the atoms of this molecule by putting coefficients in front. Don't change the subscripts, so that the left and the right side have the same number of atoms. Okay. Step 2, you're going to leave the simplest molecule until the end, right? So start with the most complex and go to the least complex. 3, when necessary, you use fractions to balance. So I will be showing you guys that, right? But if you do use a fraction, you must multiply by the denominator of that fraction to get everything into the smallest whole number ratio at the end for the balance equation. If there are polyatomics in your equation, you count the polyatomic units as units and don't separate them into individual atoms, right? So I'll show you what is meant by that as well in our examples. Okay, so let's go straight to the examples so I can show you guys how to use these steps to balance the equation. Okay, so let's do this one together. I'm going to write a balance equation for the reaction between solid cobalt-3 oxide and solid carbon to produce solid cobalt and carbon dioxide gas. So as you can see, we need to translate, right? We have to translate what is cobalt-3 oxide, right? And what is carbon dioxide. Okay, you guys know the naming now. Okay, you also know your polyatomics, or you should, right? And so this should not be a problem now. So cobalt-3 oxide, remember the 3 in parentheses means that the cobalt is 3 plus, okay? And oxide, right? Oxide is a monatomic anion. Oxygen is 2 minus, right? Because it's in group 6A. So you got a 3 plus and a 2 minus. How do you put them together so that they're neutral? You'll need 2 cobalts and 3 oxygens. So the formula there is CO2O3. Okay. So let's go to the board and write that down. Okay. So we have cobalt-3 oxide, CO, right? We need 2 of those and 3 oxygens. Okay. So that you have it. Remember, they have to be neutral, right? Cobalt is 3 plus, oxygen is 2 minus. And it's a solid state, it tells you. And solid carbon. So carbon solid, okay, will produce cobalt solid and carbon dioxide. You guys know what carbon dioxide is? CO2 gas. Okay. So as you can see right now, the cobalt's not balanced, right? We've got two cobalts here, one cobalt on the right side, and the oxygen's not balanced, right? We have a total of 3 oxygens on the left side, total of 2 oxygens on the right side. Okay. So those are not balanced. Okay, we use our steps. It says, step 1, start with the most complex compound, which is the compound with the most different types of atoms. It's gonna be that one, isn't it? That's most complex. We can compare these 4. So put your finger on it. That's what I do. And I start to just balance from left to right. The first atom I see is CO. So I'm gonna balance the cobalt. I got 2 cobalts total on the left side. And I only got 1 here. So I need to put a 2 in front here, right, on the right side, so that I now have a balanced cobalt. Then I go to my oxygen, right? And oh, I see that I got 3 oxygen on the left side, okay? But I only got 2 oxygens here, okay? So let's see what I need to do. Perhaps we can use fractions, right? So I got 3. So we got, the 3 oxygen on the left side. So here we're going to do fractions, right? We got 2 oxygens on this side. So we have to set up, we have to put something here. And let's call that X. Okay, this is how you're going to set up this fraction. Okay, so X times 2, right, has to equal to 3 oxygens on this side. Okay, and then you solve for X, right? So X times 2 is equal to 3, then X is equal to 3 halves. Okay, so what we figured out is the fraction we need to put here, which is 3 halves, right, in order to balance the oxygen. Okay, so on the left side is now 3 oxygen. 3 halves times 2, everybody, is also 3. So we have now successfully balanced the oxygen by using the fraction, right? So now, got our oxygen balance. Okay, the last thing we touch is this. We need to now balance the carbon, right? That's the only thing that's not balanced. So that's why we end with the simplest one, right? We end with the simplest one. It's carbon. There's 3 halves carbon on the right side. So we need to put also 3 halves in front of carbon, okay? So now all the atoms are balanced. However, you still have fractions in your equation. So remember that last step, right? It says, if you use fractions, you got to multiply out by the denominator to get to the whole numbers, okay? So the denominator here is 2. So that means we need to multiply all coefficients by 2 to get rid of the fractions. So here, the coefficient is an implied 1, right? So 2 times 1 is 2. So 2 CO2O3 solid plus 2 times 3 halves is 3, right? Then 2 times 2 is 4. 2 times 3 halves is 3. Okay, so at the end, right, we have 2 CO2O3 plus 3 carbon goes to 4 CO plus 3 CO2. Okay, and we can check, right? I would always do this. Check. How many cobalts do I count on the left side? 4 CO. Oh, here's 4 CO. So that checks out. It's balanced. Let's count the oxygens. 2 times 3 is 6. 6 oxygens on the left side. 3 times 2, okay, this is a big O. 3 times 2 is 6, so that's 6 oxygens. That balances out as well. And then we count the carbons. 3 carbons on the left side and 3 carbons on the right side. Okay, so I always do that check to make sure my equation's balanced. So that's it, right? Okay. All right, so the key thing here in this problem, right? You guys got to know how to name these compounds, right? Because it's giving you words now. So that was, that's one of the tougher ones that it doesn't just, have the chemical formulas for you. You have to generate it from the long name, right? So make sure you practice that. Okay, let's keep on going. This one, it says, write a balance equation for the combustion of butane, which gaseous butane. So C4H10, a fuel used in portable stoves and grills, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. So it really is telling you exactly the state of matter too, right? And so let's generate the equation before we balance it, okay? Right. So C4H10 gaseous, okay, plus oxygen gas. Remember, oxygen is part of Hofbrinkel, right? So it's O2, right? It's diatomic, yeah? And combustion always forms carbon dioxide and water, right? So gaseous carbon dioxide, CO2 gas, plus water gas, H2O. All right, see, we translated it to chemical formula, right? And so we got our equation here. Now we need to balance it. Okay. So again, step one, what's the most complex molecule of these? This one, right? Because it has 2 types of atoms and 14 atoms total. So it's by far the most complex, okay? Put your finger on it and count how many carbons. 4 carbons total on the left side. How many carbons on the right side? Just 1, so I'm gonna put a 4. Now I balance my carbon, right? Then I go to the next one. Got 10 hydrogens on the left side. On the right side, I see how many? Just 2 hydrogen. So what is the factor? How do I get to 10? 5. That's 5 times 2 gives me 10 hydrogen, right? Okay. And the one I last touched was this compound, right? So I continue there. And only thing that's has not been balanced then is the oxygen. So we have 5 oxygens here, and we got 8 oxygens here. Oh, so that's 13 oxygens over here. We got 2 oxygens over here, right? That's not balanced. And that's also, you know, there's not a whole number of factor that can like rectify this. So guess what? Fractions again, okay? So put the X, right, in front of the simplest compound, right? Simplest molecule, which is O2. So that's where your variable X should go, okay? Because remember, we need to end the simplest molecule. So now you're going to say X times 2 has to equal to 13. See, that's how you set it up. So X is then 13 halves, isn't it? So that's how you know that the coefficient here is 13 halves. Okay. So you see how easy it is. If you use fractions, you can basically immediately balance the atoms, okay? So I really highly recommend that. Okay, so now everything's balanced, but they're not in whole numbers, right? So we got to multiply out by the denominator of the fraction. It's 2 here, so we're going to multiply all coefficients by 2, right? Everybody. This is a 1, so you're going to have 2C4H10 gas. 2 times 13 halves is 13. You get 13O2 gas. Goes to 2 times 4 is 8. CO2 gas. Plus 2 times 5 is 10. H2O gas. Okay. All right, and then we're going to check to see if we have balanced the equation, right? So let's count carbons on each side. 2 times 4 is 8, so I got 8 carbons. Oh, 8 times 1, so I have also 8 carbons here. So carbons balanced. I'm going to count hydrogens. 2 times 10 is 20 hydrogen on the left side. Over here, 10 times 2 is 20. So I got 20 hydrogen on each side. That's balanced, right? Then I'm going to count the oxygens. 13 times 2 is 26 oxygen. Here I have 8 times 2 is 16 in water, right? In CO2, 8 times 2 is 16. And then in water, 10 times 1. So 16 plus 10 is 26 oxygens. Okay. All right, so everybody's balanced. Okay. All right, let's go to the next problem. Okay, let's do this one. Write a balanced equation for the reaction between aqueous strontium chloride and aqueous lithium phosphate to form solid strontium phosphate and aqueous lithium chloride. Okay, so this is nomenclature, right? You guys have done this already. This is that worksheet. If you need review, then that's where I would point you to, right? Is the nomenclature lab that we did, right? All right, so strontium chloride, you should know is SrCl2, right? Because you know chloride is 1 minus and strontium is 2 plus because it's in group 2A. So you need 2 chlorides per strontium, right? So let's write the equation SrCl2 aqueous plus aqueous lithium phosphate. Okay, lithium is in group 1A, right? So it's 1 plus. Phosphate's one of your polyatomics. This is why you need to know the polyatomics. It's 3 minus. So lithium is 1 plus, phosphate's 3 minus. So you need 3 lithiums per 1 phosphate. You write Li3 phosphate is PO4, right? 2 forms, solid strontium phosphate. This one's aqueous. Forms solid strontium phosphate. Okay, so strontium is 2 plus, phosphate is 3 minus. So I'm going to need 3 Sr and 2 PO4. Okay. To have it be neutral, right? And that's solid state. Plus, the second product is lithium chloride. Lithium is 1 plus, right? Cl is 1 minus. So it's just 1 to 1. Lithium chloride. And aqueous. Okay. All right, everybody. So that's our equation, right? Now we got to balance it. Okay. So here, the last step says, if you're balancing polyatomics, don't break it up into atoms. Just keep the polyatomic as a unit. So this is how you should think when you see PO42. Don't think of it as 2 phosphorus and 8 oxygen, because that's really confusing. Just think of it as 2 units of phosphate, and that's how you balance it as well, okay? So obviously that one's the most complex, right? So we're gonna start there. Balance the strontium. There are 3 strontiums on the right side, so we need to put a 3 here. And then there are, again, right now, 2 phosphates, so 2 units of PO4. So I'm gonna look at PO4 on the other side. Hope I see that. There's only 1 unit here, but you need 2, so I'm gonna put a 2 in front of there. Okay. All right, and the last thing I touch is this, so I'll continue here. 6 lithium. Okay. I look on the other side. That's just 1 lithium, so I put a 6. Okay. And then I count chlorides, right? 6 chlorides here, 6 chlorides there. All right. So you guys see, when you have polyatomics, right? Don't break it up. Just keep it together. Okay. I'm going to stop here for chapter 4, lecture 1. We'll continue with the rest of chapter 4, lecture 2, at a later time.